I3D Lab from IISc Bangalore is delighted to announce a first of its kind hackathon for persons with special needs as part of the India EU-ICT Collaboration.
Our motivation for this work are the users with severe speech and motor impairment. They belong to the most isolated section of the disability spectrum. They can't use speech for communication or limbs for movement and manipulation. Persons with severe speech and motor impairment are confined to wheelchairs because of involuntary muscle control and depend heavily on caregivers for any kind of everyday activities. There are numerous assistive solutions available, like head wand and mouth stick for writing and interacting with touchscreens, and alternative and augmentative communication boards for everyday needs. But these solutions are physically demanding and exhausting. They rely on voluntary motor and muscle control, which is difficult for our targeted end users. The affordability and accessibility of these solutions also poses a challenge to our end users. So the users with SSMI have to rely on manual eye tracking based communication, where a caregiver or a family member has to physically hold an eye spell chart in front of the users and manually analyze the point of gaze of the user on the chart to make sense of what the user is trying to say. This process is time taking and error prone. It is also physically tiring for the caregiver and adds to the fatigue and stress. For more than 2 decades, researchers have worked on exploiting the familiarity of the targeted users with eye gaze pointing for building eye gaze controlled assistive solutions like robotic arms and wheelchairs. Many of these solutions focus on users with specific medical conditions and use invasive and expensive hardware. These systems often require calibration and training for correct usage, and many of these works are not evaluated or tested on users with different range of abilities. When working with robots around humans, ensuring the safety of humans is crucial. Researchers have come up with different safety strategies which are evaluated in simulations and controlled lab environments using multiple depth cameras and other expensive hardware. Most of these works are done for bulky industrial robots. In the assistive space, the works are evaluated mostly by expert and healthy users. Our research objective is design and evaluation of an affordable, safe, and gaze-controlled human-robot interaction system for persons with severe speech and motor impairment. The videos show the end users using our earlier work on eye gaze-controlled robotic arm for pick and place and reachability tasks using commercially available eye trackers. To make the proposed system affordable and accessible to a wide range of targeted users, we used a deep learning approach for appearance-based gaze estimation, which gives eye gaze points on the screen by using the RGB images from the inbuilt web camera of the laptop. This approach was completely non-invasive, user-agnostic, and required no calibration. For our case, we are using a tabletop robotic arm that has small operating torques and velocities. Given the small form factor of the robot, the problem of detecting and avoiding any collision with humans to ensure their safety is narrowed down to detecting and avoiding collision with hands in the robot workspace. We used a robust hand tracking solution from Google called MediaPipe Hands. It can detect human hands at 30 frames per second while running on ubiquitous devices like laptops and smartphones without any high computational requirements like GPUs. The experimental setup used to validate the proposed system comprised of 4 OptiTrack cameras for constantly monitoring the distance between the robot end effector and the user's hand. The task for the users was to use eye gaze controlled user interface as shown on the bottom right to make the robot reach the target location by dwelling on the screen for half a second and using the 4-way control for precise orientation if required. Our first approach to safety was a naive geometric one, where the human hand is approximated as a circle, and if the hand circle intersects the trajectory of the robot, the safety algorithm provided a modified path based on the level of intersection. The second approach to ensuring safety was a more intelligent one. Here, the robot workspace has been approximated as a 2D Markov decision process grid. The grid cells occupied by hand are designated as obstacle and given a respective negative reward, and target locations are given a positive reward. The optimal robot trajectory is obtained as a result of a value iteration algorithm trying to maximize the overall utility based on the best possible actions the robot should take at each state. This approach allowed us to accommodate any uncertainty in the robot motion caused due to the errors in the robot workspace to screen mapping. The intelligent algorithm gave a more conservative or longer path for higher uncertainties. The same approach can also be used to get safe navigation in case of a moving hand situation, where the algorithm keeps a note of the historical positions of the hand while calculating the optimal path to the target. The intelligent algorithm also provided robot trajectory in case of multiple obstacles present. We evaluated the safety algorithm in multiple simulated scenarios of hand position and orientation in the robot workspace. The results showed that a longer navigation path and higher minimum separation distance was obtained for increasing uncertainties. We also performed user trials with the end users with severe speech and motor impairment. We found significant differences in task completion times of the end users and the healthy users. Both the user groups improved their performance in the subsequent trial. The intelligent algorithm could maintain a smaller minimum separation distance as compared to the circle-based geometric approach. This video shows a healthy participant performing the task. The right window shows the motion capture scene of the same. User dwells at a particular location on the screen and the robot moves to that target location, avoiding the user's hand. We have extended the proposed human-robot interface to let our users drive a toy car using their eye gaze on a screen-based augmented reality interface. The users can look and dwell for half a second at the four buttons to move the car in that direction. This interface can be used to train the users to practice everyday tasks and activities. This system can help and support the caregivers and family members by taking some load off of them and providing an engaging edutainment activity to them. We are organizing a workshop for the end users using the proposed human robot interface in October. Thanks for your attention.